Well, we can go ahead and get started, and then as folks trickle in, I'll just ask my co-hosts to admit them. But thank you all for joining today. Today's webinar is focused on real-time AI processing at the edge. We're really excited about this topic. This has been something we've been working on for a while, and we're excited to really demo different capability for you, including running a computer vision model on an NVIDIA Jetson Nano to process video in real time, and then also machine learning model that's going to analyze some data from atmospheric sensors. So this should be a pretty exciting and engaging presentation. I think you just saw we're recording this just so that we'll be able to send out the webinar after for folks who aren't able to attend. If you have questions, please post them in the chat. Everyone's voice permissions are restricted for now, but we'll definitely be taking questions at the end. So feel free to send them through as you have them. So today's presenters, I am joined by my colleagues, Brett Helliker and Samuel Dave. So Brett is an engineer with a background in systems, IoT, and applied AI and machine learning, and using sensors to create data-driven insights to solve real-world problems. His experience ranges from working at startups to defense to research institutes, implementing solutions from space systems to wind turbines, breweries, and everything in between. He has a master's in aerospace engineering from Cal Poly San Luis Obispo. And so Brett is very excited for this topic, given what I just shared. And then Samuel is the head of machine learning engineering here at Modzy and a core maintainer for chassis.ml, one of our open source MLOps projects. He leads Modzy's machine learning engineering team in developing tools that make it easier and faster to get models into production. Samuel has a Master of Science in Computer Science from University of Southern California and a Bachelor of Science in Chemical Engineering from UCLA. So with that intro, like I said, questions in the chat, and I will turn it over to Brett to kick things off for us.
Great. Yeah, thanks for the intro. Like Kristen said, we're super excited about running this real-time processing of AI and ML models at the edge. Because, I mean, as you all know, at Modzy, we develop tools that make it much faster, much easier, much more reliable to run AI and ML models in real world situations, getting out of the lab, out of the experiment, and turn them into real world. We've got a variety of tooling for running AI on the cloud, on-prem, in distributed situations and air-gapped situations. But now we're tackling running it on constrained devices at the edge. And I think this is one of the hardest problems that we've had for a few years, and we've made some immense progress. So yeah, we're very excited to share it with you. To get started, I think first, just bear with me, but we want to talk a little bit about what is AI at the edge. And to do that, I'm going to jump into kind of a brief history of computing, how we got to where we are, kind of what the past looked like. So we're going to go all the way back and just start in the early days when computers were really big, really expensive. There were only a few of them, and everyone just worked on these mainframes with terminal input devices. The terminals or consoles were very dumb devices. Each were connected to that central computer essentially directly, like they were wired in. That computer was in a room, you were all in the same building, and all processing occurred basically in batches. Like you entered your program, you actually typed in a program, the computer would parse that program into memory, and then it would execute it on any data that you had and return the results. Very batch process. It would dump everything at the end of that and allow the next person to reserve time for use on that mainframe. Then we entered the PC era, the personal or desktop computing era. Computers were now small enough and powerful enough that individuals could have them in their homes, and they could actually process a lot of data locally instead of waiting for your turn at that big shared mainframe, shared terminal system. But it was incredible, but in contrast to before, communications and infrastructure hadn't quite caught up. So now we're transmitting, we have amazing power locally, but in order to transmit it to the larger computers, we're dealing with 9600 baud modems transmitting data over ancient copper wires. So we hadn't quite caught up, and now everything is highly distributed, and we don't really have that ability to synchronize and share as much. Suddenly, mobile era or the cloud era, internet speeds have vastly increased. Cellular networks are ubiquitous and pretty darn fast. People are starting to own multiple devices. They have multiple devices right on their body, let alone on their desk or in their car or at their work. And they want those devices to be synchronized everywhere. They want that data to kind of flow back and forth. And so we start seeing a reemergence of that central computing model, where stuff is at least stored in the cloud. But combine that with, at least at first, smartphones and smart devices were actually a step backward in terms of computational capabilities, right? You weren't running huge GPUs. You didn't have water-cooled towers sitting in your pocket. So we were taking a step backward. So now not only are we transmitting data to that cloud, but we're relying on those cloud instances to process a lot of that data and then return the data back to your device over that really fast network. So it's kind of been a tick-tock here until we enter final era, the edge era. One of the biggest changes that we see in the edge era is that of, we're moving from batch, we're moving from collectors pushing data up or just running batch jobs on your desktop to just absolutely continuous data transmission and processing, and the boundary between processing locally and in the cloud is starting to blur. We just have data flowing back and forth. We have collaboration on where that processing is going to best occur. And we can kind of shift that around based on circumstances. Like if the network is unreliable, we might want to shift it to process locally. If the data is immense or the processing requirements are immense, we might want to shift that back up to the cloud. It's just a continuous flow, and the boundaries between these various components have immensely blurred. So this is the area or the era that we're entering now. We're still kind of in its infancy, but we're jumping into it with both feet. And the interesting thing about this era is that as the devices on the edge and the network to the cloud get more and more advanced, we want to run more and more advanced stuff on these little autonomous, IoT devices or cars or video cameras. And we want to run more advanced algorithms than we used to. So we want to start running AI and we want to start running ML algorithms on the devices at the edge. So with that said, I think I'll let Samuel start talking about some of the considerations of running AI at the edge. Take it away.
Thanks, Brett. So yeah, why might you want to do such a thing? Why would you want to run AI models at the edge rather than, for example, transmitting your data all the way over to the cloud, running your processing there, and then waiting for the results to come back? Well, there's a few reasons why you might want to do this. Security, you might have patient data in a medical setting or just other sensitive data that you don't feel comfortable transmitting all the way over to the cloud. Latency, you might have applications that need those inference results in real time, and so you don't have the luxury of taking on that additional network latency of transmitting the data back and forth. And finally, you might have situations where your edge devices are completely offline, and so you still need AI models to process in those settings. So a few reasons why you might want to do this sort of thing. Next slide, please. So when we talk about edge devices, it's actually an umbrella term, and it covers a wide range of devices. So the way that we like to start to think about breaking these down is along two sort of factors. One is the amount of computational power on board, and the other is the amount of network connectivity that particular device has. And so at the top right of this diagram, relatively high computational power on board, high level of network connectivity. We refer to this as the near edge. And as we start to move out from that near edge along either axis, either computational power or connectivity, we start to move towards what we refer to as the far edge. Next slide, please. So using these criteria, we can sort of start to roughly bucket these devices. The amount of power you have on board and the amount of connectivity sort of determines the use cases that you can and cannot support. And it really governs the reasons why you might actually want to deploy an edge model to an AI model to an edge device. So I'll give a couple of examples, starting with the iPhone 13 near the top of the diagram. Most of the time, these devices are connected to the internet, pretty decent computational power on board. A lot of the use cases that you would consider aren't necessarily critical, meaning sort of life or death scenarios. So you do have the option, if you want to, transmit your data and run your AI processing in the cloud and wait for the results to come back. If you were to deploy an AI model to that device, though, the reason would most likely be for speed. You might have an application that needs those inference results in real time, and so you can't take on additional latency. Whereas, if we go down a little bit in the diagram to the Tesla, if you put that in self-driving mode, sure, speed definitely still important, and it can, or in some situations, it'll be connected to the internet, in others it won't. But in the situations where it's not connected, those AI models still need to process no matter what, because they're doing things like detecting stop signs, seeing people in front of the car. And so, those things need to be running at all times, no matter what happens. And so in these sorts of scenarios, reliability is really the most key factor. So now we understand sort of the why. Why might we want to be, deploying AI models to the edge? But it turns out that in practice, it's actually quite difficult for a variety of reasons. For one, you need some sort of mechanism to be able to remotely deploy models to that edge device and get them up and running. As we mentioned on the last couple of slides, there's a lot of diversity in these edge devices, right, as far as hardware resources. And a lot of them actually use a different type of processor called ARM processors. And so applications need to be built accordingly, taking all of that into account. Finally, or not finally, third on the bottom left, we need some sort of interface, ideally some sort of easy to use standardized interface to be able to easily connect to input data sources. Maybe you've got different sensors on board your edge device, cameras, microphones, thermometers, anything else. We want to be able to easily get that data over to our machine learning model running on that device. And we also want some ideal standardized interface to be able to get those inference results out. And so in whatever application you have, you can actually do something with those results. And then finally, on the bottom right, as we talked about in the self-driving car scenario, there are many situations where no matter what, those models need to continue to keep processing. And so these are some of the challenges associated with actually deploying AI to the edge. And we feel that Modzy Edge addresses all of these situations. And so I'm going to hand it back over to Brett to talk more in detail about that.
Yeah, no, we're super excited because, now we're introducing Modzy Edge, and we think we've tackled every one of those hurdles and even, a whole lot more to make it fast and easy to install and deploy models. It takes just a few minutes to deploy that model, depending on network speeds and all that. But really, you can do it with just a couple of terminal command lines, as long as you're running, some variant of Linux. We've made it as universal as possible, so it's nearly any AI model, whatever infrastructure you've used to train it, whatever you've used to, whatever architectures you've used to develop that model, we can package it up into a compliant container that will run, and it'll run on just about any input, video data, IoT data, audio, what have you. And it'll run on just about any device. I mean, we've optimized for ARM and x86 at this point, but we're expanding that forever. But you don't need a GPU. You don't need huge quantities of RAM. We've done everything we can to really optimize. And beyond our system, it just depends on what model you're running, what sort of hardware you'll need. Also, one of the biggest parts of Edge that you really need to pay attention to even more than typical models is drift and staleness. So we have made it as easy as possible to update, to retrain and then update that model that is running on that edge device. It's as simple as creating a new version and then marking that for distribution to the other devices so they can download it the next time they get network connectivity. And of course, running offline is essential. You do need to be online to get updates or to synchronize, transmit data and results back and forth. But beyond that, once the model is downloaded, it'll run offline in perpetuity. So we've put a lot of work into this, and we can get as technical as we want, but we'll get into some of those maybe later on in a tech talk, and we'll try to keep things a little bit high level here. But I would love to just jump into an actual concrete example right now. And I'm gonna talk about environmental sensors, just because it's kind of the hello world, the simple situation that people can wrap their head around. But when I talk environmental sensors, what I'm thinking is like small, cheap, numerous, capable of recording indefinitely without any human intervention, because like Selma showed off that chart earlier of low power versus low connectivity. And for most environmental sensors, we're dealing with the worst of both worlds. Like we are sitting out in a field for 2 years, so we need to run on a battery, very low power. And then because we're out in some sort of remote situation, we have maybe 2G connectivity at best, or maybe somebody comes by to synchronize once a day or once a month or even once a year to synchronize that data back and forth. So worst of both worlds, very low connectivity, very low power, but we still want to collect data and run inferences. And just to kind of really put a concrete spin on that, like imagine remote facilities like tops of wind turbines, bottoms of bridges, water treatment facilities, dams, or in the numerous use cases, we could think, you know, smart grid applications, solar farms, weather monitoring. These are where we need hundreds to tens of thousands of devices all simultaneously running. Not a situation where a human would want to go out there and monitor and update them all. So what we're looking at here is a Raspberry Pi. The beauty of this is that it's simple, it's hobbyist class hardware, there's no GPU, it's got some pretty limited connectivity, but the beauty of this thing is that it's about 30 bucks. And so I want to build a model that'll run on this. As I mentioned, I want to build kind of an environmental sensor. So again, kind of as the hello world of sensors, I'm going to build an AQI sensor. That's air quality index. You've probably seen it these days in your weather app or on your Google Maps app even. If you live in a place, you know, maybe on the West Coast where we have to deal with fires, the AQI is frequently at the top of your mind. It essentially rates the health of the air that you're breathing. And so if AQI is high, I might not even want to leave my house. If AQI is middling, maybe I don't want to go for a run or do some strenuous exercise. So for this sensor, you know, I could calculate AQI with a couple of sensors very, very simply, but what I want to do is actually predict what my AQI is going to be in the next hour or two. Again, maybe I want to go for a run, maybe I want to start getting dressed, getting prepared for that run. So I want to predict what's going to happen in an hour. So that's why I need a piece of hardware like this. I need a couple of sensors. The blue one on the left is a particulate matter sensor. So, you know, if you've ever seen PM 2.5, PM10, those sort of ratings or gauges, this is the sensor that's going to detect those. On the right is a simple CO2 temperature humidity sensor, just to kind of augment the stuff that I'm sensing and adding into that algorithm from the particulate matter sensor. I combine these and build a little box and add a nice little battery, helpfully branded. But this is a standalone device that will simply record all of that data every time it's turned on. Because, you know, as any data scientist will tell you, a model that you train, if I want to predict an hour from now, it's only as good as the data that I'm feeding into it. So for this model, I just set it up to run for about a month, just collecting data continuously. What we're looking for here is to collect patterns and to collect, you know, dependencies between the different, you know, does temperature cause CO2 to vary? Does CO2 influence the particulate matter? Does humidity change things? I'm looking for, you know, time of day. Is there a cyclical pattern? Is noon the worst time of day every single day? Does everything clean up at midnight? If I could run this for a week or a month or a year, I could start seeing, you know, weekday patterns, is air quality worse on Wednesdays? I could see seasonal variation, like is air quality better in the winter or after a rain? And we could start, collating and correlating those different variables and getting better and better results. But for now, I've got about 30 days of data. So we're going to train a model. After a lot of collaboration with my colleagues, we decided on an SVR, or a support vector regression model. We're not going to get into the technicalities here of why I chose that. Suffice to say, it generally works well with cyclical time series data like we're seeing. If you really want to know, talk to your local data scientist about any side effects of using this particular type of model. This chart is not super interesting. The gray bar is the actuals, and then I'm altering different variables, different weightings, different optimizations of that model as I build it so that I can just choose which one I think is best. When I've chosen it, I'm getting an actual and predicted line that are very, very similar. So I'm going to go ahead and use this model and train it, or use this version of the trained model and try it out in production. So this really is where Modzy and some of our tooling comes into play. For the easiest deployment, I'm going to take that model, which at this point is just Python code and variables living in a Jupyter notebook, and I'm going to use Chassis to actually package that model up and then create a Docker container and then upload that Docker container to Modzy. This does take a few minutes to do, so I'm not going to do it live here, but you can go. We had a tech talk demonstrating this very thing, I don't know, a month ago or so. So we can, if you have a question about that, we can point you to the recorded video or walk you through it ourselves. But once I have that container produced by Chassis, I'm going to upload it to Modzy and have it, protected by Modzy in terms of security, have it create an API endpoint, have it monitored, have it add all the documentation around it, like all the typical features that Modzy will do in the cloud. But most importantly, Modzy will now make it available for downloading to edge devices. So from here, let's see if this will work, but I'll actually go live into an instance of Modzy. We can see our nice model library here. And if we go to My Models, we see that I do have an AQI sensor built for an ARM. That's another feature of Chassis. It actually builds this particular model specifically for an ARM processor. But what I want to do is go into Edge Devices, and I want to create a new device group. This will be a group. I only have one right now, but let's say I had a large group of Raspberry Pi sensors. So I'm just going to say AQI prediction group, and then I'm going to add a model. I want that AQI model that I just demonstrated. Oops. Add a model, AQI. I don't know why I can't click that. There we go. Don't use the mouse. But that's all there is to it. This designates that that model is going to be used on this device group. And I can add as many models as I want. We see that that device group has shown up. And so now we have the ability to manipulate it, to monitor it, to create everything. I'm not going to have any devices yet. So the first thing I want to do is create a device token. For security purposes, I can set expiration time. I can set number of uses. Generally in testing, I'm going to say, oh, I can use this 10 times and I can use it for the next 12 hours, just because I know for testing, I'm going to be doing things a lot. But in this case, we don't have to do any of that. So I'm going to create this token. It can only be used for that time period, only be used for that number of uses. And again, Modzy is going to create everything it can to do things very, very simply. So all I have to do is say, hey, I'm using an ARM chip and I want to generate those commands. From here, I copy and paste these 3 lines, these 3 commands. The device itself, as long as it's on a network right now, will reach out over the network, download a small, very small binary that Modzy's created specifically for that ARM64 chip. It'll run that. That will tell it to download the specific models that we've designated. and then it'll start running those models immediately. Again, that's another thing that does take a few minutes. So from here, I'll jump back over. We're going to start getting live data, live predictions. Again, I don't want to bore you with showing you the live terminal output. Here's a small copy and pasted capture of it. We see here the current, it's not really an AQI, it's a scaled version of it, but 642, the predicted is 612. And then we see, every 5 minutes, we're taking a new reading. By the time about an hour crosses, we're down to 612, 611 as our current, which matched our next hour prediction. So our model's working pretty well. On the right-hand side, I actually have a light. So this will turn, the left side, the results, those can be synchronized up to the cloud. Maybe you create an iPhone app, maybe you have fun with that. But on the right-hand side, maybe I just want to hang this on my doorway. So now I know just at a glance, hey, in an hour, is the air going to be breathable or not? Green means great, go for it. Red means, hey, you might want to think about that. So that is the full process of training that model, to deploying that model, to getting it on the edge and running live predictions. I know this is very simple, very hello world. So we're just doing, IoT data, just plain time series tabular data. So now I'll turn it over to Samuel, who has a much more interesting data demo of using computer vision on the edge.
Yeah, thanks, Brett. So just to kind of set the scene, sort of imagine you are at a construction site and maybe you are the supervisor and you've got a policy in place where folks need to be wearing hard hats at all times for their safety. But as we know, unfortunately, folks don't always necessarily follow the rules, or maybe they just forgot. And so maybe we want to do something like sign on or turn on a siren to let folks know that they need to put their hard hat on whenever that's detected. So could you hit play on the video, please, Brett? All right, so this is the model that we're going to use. It uses the MobileNet SSD architecture for folks who are familiar with that. This is not running on the edge right now. I ran this inference on my laptop, but I just wanted to show you what exactly the model actually does. It detects people, hard hats, and it also detects vests, but we're not going to be using that actual capability today. All right, so what I've done is gone through a similar process that Brett explained. So I took this model, I containerized it, I deployed it to Modzy, I then configured an edge device group, and I assigned this model to that edge device group. And then we're going to use that token that was generated for that device group on our Jetson Nano, which I'm going to show you in a second, and everything is going to run there. So let me go ahead and switch to my other camera here so I can give you a closer look at my little setup. Give me a second. All right, so here is the NVIDIA Jetson Nano. If you're not familiar with it, it's pretty much just a small computer with the GPU on board. That GPU is going to allow us to run the computations required for deep neural networks more efficiently. And then this webcam here is going to be capturing video frames, which are going to send over to Modzy Edge. And if I am detected by the model, but I'm not wearing a hard hat, then we're going to go ahead and turn on this siren that I have right here. And then when I put the hard hat on, hopefully the siren will turn off. All right, so let me switch back to my regular camera and let's go ahead and kick this off. Give it a second to spin up. All right, so I'm not wearing a hard hat and it looks like the siren did turn on. So let's go ahead and put one on and it should turn on slightly thereafter. And looks like it did. All right, and now let's take it off and see if the siren comes back. And looks like it did. All right, so let me go ahead and turn this off so it doesn't keep making that noise. 1 second. So to sort of recap, everything that you just saw is running on that tiny little Jetson Nano device, and all of that is made possible with Modzy Edge. So just kind of a toy example, but wanted to give you guys a sense of the sort of things that are possible with this technology. So to kind of recap some of the key characteristics of Modzy Edge, pretty easy to get up and running. So just a few commands on the actual Edge device to get Modzy Edge up and running. And prior to that, you do need to configure your Edge device group through the UI like Brett showed. But as he demonstrated, that's not too complicated either. As far as flexibility, we support any model type. You can use pretty much any framework. We can take any type of input data if you've got a microphone or a camera on board, or anything else, text data. All of that is supported. Pretty easy to update. So because we are managing our models in that centralized platform, if you want to deploy a new version of a model or a new model altogether, all you got to do is deploy it to containerize it, deploy it to Modzy, and then you can make it available in your Edge device group. You restart Modzy Edge on your actual device, and it'll go ahead and pull that model and get it spun up and ready for inference. It's really that simple. And finally, as long as you've got the model deployed to the Edge device, it can run offline, no problem. Next slide, please. So to go into a little bit more detail of how all of this is working, on the left is the Edge operations dashboard. That's the UI component where we configure our Edge device group. Within that device group, we can have numerous Edge devices registered, and we can have numerous models enabled within that device group for deployment to those devices. Now, on the right, on the actual Edge device, we'll go ahead and start on the bottom. We can support different processor types. We can support models that require GPU access, and we can support different operating systems. So a ton of flexibility there. When Modzy Edge spins up, it's going to go ahead and pull models down that have been enabled within that device group. It'll spin them up for inference and expose both the REST and gRPC API so that it's super easy for you to integrate things on both the input and output side. So you can be capturing your video frames from your webcam. You can easily start submitting them to that model, and you'll, through a standardized interface, be able to get those inference results back out so that you can start doing things like turning on a siren or anything else that you want to do with those actual inference results. Next slide. So continuing with that sort of flexibility point, we support pretty much any combination, almost any combination of devices, processors, and operating systems. If you're running on a Jetson Nano or a Raspberry Pi like we demonstrated today, you can do so, but we can support smart cameras. Maybe you've got computer vision models running on a drone tracking vehicles, just as an example, or on a more powerful edge device like an HPE Edge line. All of this is supported by Modzy Edge. So as far as use cases go, we showed a couple toy examples today, but the possibilities are really endless, and we'd like to kind of point out a few examples in different areas. So starting on the top left, maybe you're at an airport and you've got different cameras set up all around, and you want to detect suspicious activity. So you can have a model running that does that, and as soon as suspicious activity is detected, maybe we alert TSA so that they can react accordingly. At a shipping port in a facility, maybe you want to do things like cargo container scanning. Maybe you want to have some sort of safety issue alerting going on, similar to that hard hat detection model we just showed a couple minutes ago. Customs and border protection. Maybe you've got a border and thousands of cars are coming through, and you'd like to have cameras set up that can find license plates within the video frames, and then actually go ahead and read those license plates, submit the license plate number to a database, and then check them for whether or not they need to be stopped, and an officer can be alerted immediately. And then at a hospital or a clinic, maybe security is more of a concern here. And so rather than having to transmit patient data all the way over to the cloud for processing in any AI models that you've got running, moving those models closer to the edge really mitigates that risk of someone being able to intercept that data or manipulate that data.
And just to even continue, monitoring stations, we already discussed a little bit, stuff like an air quality monitor and infrastructure. We can imagine a device, with an ultrasonic transmitter on the base of a bridge or on a railroad track, or somewhere, looking for cracks. We can imagine devices distributed widely, monitoring weather patterns, whether they're at the top of buildings or deep into forests. Emissions are a big thing now. We monitor them both in cities and in the environment, as well as, maybe an actual emission sensor clamped on to every single exhaust pipe, whether that's on a vehicle or a factory or wherever you happen to be emitting air pollution. We also have a lot of water quality use cases. So imagine like a sensor I was involved in where we put the sensor inside of a float and just floated it down the Chicago River once a day, and we would continuously get data and results processed right there locally as it floated down the river. Remote facilities, very similar to monitoring stations, but imagine more of a large facility where potentially people are. So the live models could save lives, could influence people's health, could just influence productivity, instances like that. But if we, similar to a bridge or a railroad, we could be monitoring for cracks in dams. We could be monitoring turbine speeds and health. We could be monitoring water treatment facilities. So whether that is the water incoming, the water outgoing, however it's being used. A lot of those sort of use cases we see day to day. Regional government offices sounds like a very funny subcategory, but this is one of the largest use cases that we see. Automated services. Imagine a camera or a scanner with an AI model running on it locally that will tell people that they've filled out their forms incorrectly. Before you ever have to stand in line at the DMV, you know that your form is filled out right. Also, it can scan that form to try to identify what your issue is and direct you to the appropriate line. Maybe one line specializes in new licenses and one line specializes in new registration. You can have an AI model doing a lot of that, just light up the arrow that says go left or right. Letter and package scanning, obviously USPS. A lot of us get a scan of our letters every single day in our email. So maybe we could run an AI model on that and let us know a little bit more about it, or maybe right within the truck so that we can have verification that the correct letters and packages are going to the correct addresses. And then one of the biggest use cases, again, of fraud, waste, and abuse ID. What we're doing here is looking for patterns, looking for transactions, looking for anything out of the ordinary, any anomalous behavior that doesn't match the typical transaction flow that you'll see in an office. And then, of course, security, similar to airports and border protection. What we're doing is loading models onto video cameras or security cameras or other devices to be able to identify people of interest, to be able to identify weapons that they're carrying, or even little things like identifying that a window is open when a storm is coming. You're going to lose your building energy, or you're going to get things wet. Little stuff like that can be programmed into these AI models. And then our last category here is my personal favorite, wearables. I worked in this space for a long time. Stuff like soldier health tracking, which can be extended out to first responder tracking, or paramedics, firemen, nurses, doctors. If you're in the field or in an adverse situation, whether it's training or real, we can monitor heart rate, breathing, skin galvanic response, and we can tell you, are you about to pass out due to stress, due to dehydration, due to just being awake for 48 hours straight as you deal with this high pressure situation. Small devices like that, as small as an Apple Watch, or maybe a heart rate monitor that you wear anyway as part of your workout routine, we can add models to those devices that will really augment that functionality. And then, of course, everybody is looking into driver behavior monitoring. This is stuff like eye tracking, being able to determine if that driver is drowsy, if they're paying attention to the road or their smartphone, or some other hazard. Being able to detect that, maybe send an alarm right there in the cab to wake up that driver, or maybe, as vehicles get more and more advanced, maybe just pull that vehicle over, let the driver have a little half-hour nap. Either way would be fine, but these are huge areas of interest and research for us. So anyway, I hope some of those gave you a little bit of inspiration for what you could use AI on the edge for. This is just, just the surface. We've seen so many dozens, hundreds, thousands of examples of really, really creative, really compelling use cases, but specifically using that AI on the edge rather than in the cloud. So I hope some of those inspired you. And with that said, I would love it if you all could let us know what you're using it for or what interests you, or just ask us, is this a valid use of running AI at the edge? Is this an interesting use case? Would it make sense? We're happy to answer those sort of questions and help guide you through the implementation details. And as you can see on the slide, we've got various trials, various free trials, and we've got all of our archive of tech talk and documentation to help you get started. And of course, join our Discord channel so we can chat about it. And with that said, I think I'd love to open it up for some questions.
Yeah, thanks, Brett. So let's go to the chat. We'll start. So someone asked a question. Can you just give a little bit more detail around security at the edge? And I think this goes back to another question that I had seen around just sort of reiterating the benefits of running the processing where data is collected.
Yeah, so I think the answer that Seth gave is an important piece, right? There's end-to-end encryption involved when we're actually deploying the models, all the way from that central sort of Modzy location to the actual edge device. You can configure tokens that will expire after a certain amount of time, and so those models won't be able to be accessed after that. And as I've mentioned a couple times through the presentation, a lot of times you might have concerns with your sensitive data and transmitting that all the way over to the cloud. That gives bad actors opportunities to be able to intercept that data. And so if you're actually running the model on the device where the data is being collected, you're really minimizing the opportunities for folks to be able to do that sort of thing.
That's awesome. Thanks, Samuel. And then another question I saw, so any other edge OEM providers Modzy's partnered with other than NVIDIA? And so Nathan was kind enough to answer with that. And then if you go to modzy.com/edge, you'll see some details around our partnership on the Edgeline 8000. Can we get a copy of presentation slides? We'll be sending out the recording of this after to all those who registered. Let me go over to some of the other questions that I had seen. So how else can Modzy be deployed? Brett or Samuel, do you guys have some more details around that?
Well, that's Edge is kind of the last method of deployment. So of course it can be deployed on any of the major cloud vendors, Azure, GCP, AWS. Those are our typical deployments, are running in the cloud, managing your models and running them as endpoints accessible from anywhere that you can get access to that. We also deploy on-prem, both air-gapped and within private instances, but not air-gapped. So either of those situations will work great. So if you're not using a cloud vendor, if you are using an on-prem system or completely firewalled internally, those are both fine for Modzy. Those are kind of the actual birth use cases. Modzy was originally built for an air-gapped system that we've since expanded. And then, of course, we're working on the edge now, and then we have just kind of a nodal architecture where you could have a central in the cloud and then mixed at the edges, whether it's an on-prem system or an edge system or another cloud. We also have that sort of deployment.
Awesome. Thanks, Brett. I see another question here too around what kind of technology is used to ingest the sensor data.
I'd say that's entirely based on the edge node itself. I don't know what Samuel's using. I'm using SPI for these sensors. I also have a UART for one of the other sensors, but that's just run. I have a very simple logging application running on mine so that it can bridge the SPI interface over to the model.
Yeah, it really depends on what type of sensor you have, what type of device you're running on. For the demo that I showed you guys, I was using OpenCV in Python to be able to read those frames from the webcam, and then just using Python to we provide in Modzy SDK, we have edge functionality that will allow you to easily be able to submit inference jobs directly. So in our case, it was video frames. And so Again, really depends on the use case and the device and the type of sensor that you've got. A lot of times there will be open source tools available for you to make that process pretty easy.
And I guess just to add on to my answer, in my case, I built, or the way I'm using the SDK is it's either binary or text. And so I'm essentially just sending a CSV of those different sensor values, PM 2.5, the CO2, the temperature, sending all those values just as a string of comma separated values, every time a reading is taken, and the model takes those and spits back out its result.
Awesome. Thanks, guys. Here's another question that we've heard fairly frequently. So what if an organization is really just getting started with adopting AI and they're trying to, do some quick win pilots to sort of prove out, the investment? Is Modzy's Edge capability, is that something that we can take advantage of? How would you answer that question?
For sure. Modzy's definitely optimized for like production use cases, so thousands or millions of users a second type of thing. But we get this question all the time, and we have a lot of customers who are really just dipping their toe into it. And Modzy has so many features that are excellent for running those experiments. Like one of the biggest things is just the speed of deployment. So like the traditional is, oh, I'm going to train a model in my notebook, I'm going to deploy it, I go talk to DevOps. DevOps tries to push it out to my half dozen devices, and this whole process takes 3 to 4 weeks or months. The beauty of Modzy is, at the end of every day, or every single time I get more data, I train that, I deploy it to Modzy. Modzy automatically pushes it out to all of the devices. And so now I can experiment with different models in production. I can A/B test, put different models on different device groups. I can see which models are running better and give me more accurate predictions. And I can do all that, on an hourly basis, just about, or faster if I want. And then not to mention all the rest of the features of Modzy, like our security and our monitoring and logging and auditing, all of that make it really easy for you to just, even if you only have one model, or even if you only have a couple of models, to utilize Modzy and get a lot of value out of it.
Thanks, Brett. And then I see another one here. Is there a simulator we can use to test the platform? I'm going to paste the link. I would encourage you, just like Brett said, at the end to sign up for an enterprise trial. It's free. And right now we're running a promotion where if you go through an enterprise trial, you can deploy your devices to deploy your models to up to 20 edge devices for free. So just fill out that form. We'll be in touch very quickly to get you up and running to test it out.
Yeah, and depending on what exactly you're testing, for instance, with that AQI model, the difference between running it on ARM and running it in the cloud is just a flag in chassis. I just say ARM equals true or ARM equals false. So in that case, I'm running the exact same model, both on the cloud, on an extra small instance in AWS, and on my ARM machine. So I can start feeding the cloud data and test out that model just with offline data or with test data that's coming through with CSVs or something, in addition to running it on the ARM device itself. So that's how I do a lot of my testing before I deploy it to the device. So depending on how you want to simulate, we have a lot of options and a lot of capabilities around that.
Awesome. Well, we're always happy to give everybody just a little bit of time back in what I'm sure are very busy days. It looks like that's not so much a question. Anything you want to say here, Brett or Brad, before I wrap, or Brett or Sawmill, before I wrap it up?
I don't know. I definitely used data infilling techniques for training the AQI sensor a little bit, because every once in a while the sensor would go offline for about an hour if I kicked it or unplugged it or something. So I definitely utilized that, and it was a huge win just because I was able to have a gapless data set despite little local issues. But yeah, totally agree with the rest of the statement. It's a big win for consumers. It's an easy on-ramp, easy test, easy way to get started.
Awesome. Well, thank you so much, everybody, for joining today. As I mentioned, we'll send out a recording to this afterwards if you'd like to rewatch it or share with anyone who you think might find it beneficial. And we hope you have a great rest of your Thursday. Stay tuned for our next webinar, which I'm sure will come in the next couple of months on something equally as exciting.
Yeah. Thank you all for your time. Hope you enjoyed.
Thanks, everyone.